Okay, good morning everyone. Let's get started. I hope you all had a good Freshers Week and stayed away from the Freshers flu as far as you could. My name is Moritz Riede. I will be teaching the first 10 lectures of classical mechanics in this term. And if I'm not here, I'm an experimental physicist working on organic semiconductors, organic solar cells, as renewable energy technology. The samples we do in our lab are pretty small, but we try to understand the basics such that something like that, a solar cell, can be realized. So this is what I'm doing in my, no, not in my spare time, but as research, and I'm not standing here. If you're interested, you can follow our group, twitter.com, and then it's AFMD group. Two quick things. Housekeeping. Usually there's a huge pile of notes up here for you to pick up. It looks like we ran out this morning. I don't know what went wrong, but there should be a couple of more notes coming in. Before every lecture, I upload the notes on WebLearn. Some of you probably have already seen them. That's also the place where you can find all example sheets, or at least the first 3 example sheets. And you might have already started working on those. This is all second years are supposed to be in the other lecture theater. Just go through this way, take the shortcut. This is first year. Anyone else, second year or third year? Okay. This is the first part. Usually pile here, pick it up, and it will be online. At the end of the week, you will notice that some parts of the notes are missing. At the end of the week, I'm usually uploading the completed notes in case you struggle with my handwriting. The second thing is, some of you have already come into the building holding their bot card long at the reader to activate them. If you haven't done this when you came in, I think Pam was standing outside and convinced some of you to hold your card very long onto the reader until it blinked green. Do it at some point, maybe tomorrow. This is how the card is getting registered in the system, and then you have access to the physics building. Okay, those were the two main points in terms of housekeeping. Now, you come from a wide range of backgrounds with different knowledge. I would guess half of them are from the UK, the other half is from around the world with different schooling systems, different experiences, and so on. So my goal is to get you up to speed with the basics. That also means that for some of you it might be boringly slow. You may have already done most of it of the first lectures in your school. For others it might be a little bit fast, and for me the challenge is always to find a middle ground, and when I go over the comments I get as evaluation of the lectures, some say it's too fast, some say it's too slow. I'll do my best, and if you've got any questions, you can usually catch me after the lecture or send me an email regarding questions on the lectures. If you've got questions on the example sheets, the best person to talk to is your tutor in one of your tutorials you have in college. Now, if you don't understand something I explain in class, or you can't read my handwriting, please ask immediately. If you are struggling, then most likely other people are struggling as well, and it's better if these questions have been resolved straight away. Now, let's then get going. Oh yeah, if you spot an error, please let me know as well. I've tried to avoid errors, but spelling and things like that can happen. Now, this is the outline of the first lecture, going over the standard things. So there are 2 groups of lectures. The course had been lectured by Professor Neville Harney before, and I took it over. So most of the slides are based on his. All mistakes are mine. The first 10 lectures, mostly 1D and 2D motions. one half setting the basics, one half of the course is collisions, collisions, and collisions. And then you will have another 20 lectures in Hillary term with Professor Guy Wilkinson. He's a high energy physicist, mostly working at CERN. This is where you can find the course material on WebLearn. It's when you navigate to CP1, that's where you can find the notes. I see some people working on their tablets, some people have their laptop open, so this is where you can find the stuff. The web page contains the suggested reading list, the problem sets. As I said, the first 3 are already up there. Furthers will follow then by the other lecturers. And the lecture slides, the one of today is already up there. I usually put them up at some point in the morning before coming to class. And then at the end of the week, I'll upload the 2 or 3 lectures we have in a week with the stuff I left out and worked out here at the Blackboard. Now, book list, recommended reading. The core of the lecture is in class, but it's always worth reading a little bit left and right. There are different examples, different viewpoints, different ways of tackling problems. This is just a small selection of books. Before you go out and buy them, please check your college library. Many have these books in stock, and also have a look online. There are lots of courses online, both written scripts and videos that give a different perspective, different ways of teaching, some that might work better for you than my style, some that might be worse. Feel free to choose whatever works best for you. So here, Introduction in Classical Mechanics, been first published in 1986. Most of you were probably not around at that point. It's a solid course, feels a little bit old and dusted, but contains quite a lot of information. Introduction in Classical Mechanics by Morin contains many solved examples, especially good for the second part of the course, Lagrangian dynamics. The third book is a good basic intro, has questions and some solved answers in there, so again, something that might become useful at some point. Then we've got Fundamental Physics by D. Halliday, R. Resnick, and J. Walker. That's not Johnny Walker, but Joel Walker. It's more than just mechanics. And then a couple of other books, Analytical Mechanics, now in the 7th edition. Similar structure to the course in this term. Has some answers, and with classical mechanics, you can do quite a lot of coding, and there's lots of stuff online where you can play with forces, simulations, and I'll at least show one as part of this course. Physics for Scientists and Engineers, as you can imagine with this general title, it's a pretty massive book, 1,500 pages, but it covers more than just classical mechanics. And last but not least, the classical mechanics based on a course taught at Imperial College. So it's probably pretty good as well for most of you. Now, as you probably can hear, English is not my native language, and most of you also have English as foreign language. There might be other textbooks around in other languages or from different background. Those were mainly written by people from the UK and the US. So if you have a good textbook you've studied with, of course ideally in English, but there might be others, please let me know. I'm always curious to find out how classical mechanics is taught elsewhere. Okay, we're nearly ready to start with the course, but before that, a quick something slightly different. Does anyone recognize one person whose resemblance is in there and what this cartoon is about? Does anyone recognize? Yeah.
If you're really struggling with life, don't put your priorities immediately on physics.
That is one potential interpretation. Physics, well, yes, physics doesn't solve everything, although most in life probably is due to some physics further down. Any other suggestions? Anyone recognizes someone who's this resembling? Yeah. Yes, exactly. That's Greta Thunberg. So the reason why I'm showing this is the world is warming, is going up, heading way beyond the goal of 1.5 degrees centigrade, and the future generations will be particularly affected by climate change, and it's unlikely that unless we change something really drastically, we can keep within the 1.5 already. And this cartoon is from a German cartoonist, because Greta started, she's 16-year-old, Swedish, started walking out from school, and that was the reaction of many teachers, that she was pointing out that something's really wrong in the environment you're in. So if that crack continues, the aquarium will be drained. But the teachers usually first concentrate on your math homework. I hope I'm not then replacing that with CP1, but it's something that the young generation is speaking up now, but the challenge is to get a voice and get heard too. And when Greta spoke in front of the US Congress recently on climate change, she was queried there on climate change, she brought along a special report of the Intergovernmental Panel on Climate Change and basically put it in front of her and said, well, don't listen to me, listen to your scientists. And, well, you all have been selected here on your promise to thrive in Oxford physics and to come out as further trained scientists. And Oxford prizes itself to lead, train the next generation of leading scientists. And with that, you carry a certain responsibility because, well, if someone tells you, listen to your scientists, you better be right. And this has been an occurring theme in science and research, that you carry a certain responsibility. And about 60 years ago, Bertrand Russell and Albert Einstein and together published the Russell-Einstein Manifesto. The QR code takes you there if you want to take a picture, but you can easily Google it. It has 11 signatories, the most eminent scientists at that time, who have 11 Nobel Prizes among themselves. And they basically, this manifesto was a response to the realization that mankind had developed with a hydrogen bomb the means of basically eradicate human life on the planet. And those scientists argued that scientists should take on the responsibility and work together across nations, across continents, across creeds to solve this challenge. And yeah, 5 Nobel Prizes in physics, 2 in chemistry, 2 in peace, and 1 in literature do those people share among each other. And probably one of the most important line that I think is still valid, this manifesto calls as human beings to other human beings that you should remember your humanity and forget the rest. So trying to solve these challenges, and I think with climate change we indeed have quite some challenge ahead. But no matter where you go and what you do, you build everything on your scientific credibility and the quality of research you do. Okay, enough of that. Let's start and move over to classical mechanics. The most common quote on classical mechanics or starting point is, of course, Isaac Newton's and the famous apple that fell at some point from a tree. Woodthorpe Manor still exists, whether the story is true or not. Newton himself told it later in his life, so most likely is true, but of course the more you repeat a story, the more elaborate it probably gets. Now, classical mechanics is the study of motion of bodies in accordance with the general principles that he put out. Basic forces, so how bodies move under the influence of forces. It's a very old subject. looking around how bodies move in, say, in astronomy, stars and planets, molecular nuclear physics, so if you've got particles colliding, seismology or geology, where the waves propagate, all classical mechanics and engineering, of course, you put together bridges and buildings along that. Trinity College, Cambridge has one of those Philosophia Naturalis Principia Mathematica around it. If you happen to have one at home and want to auction it off, there was one auctioned off in 2016 for $3.7 million US. So there are not that many around, and it's one of the foundation works in classical mechanics or in physics in general. Now this list, I could go on much, much longer, and you will find many examples there. This course in particular will cover, or the classical mechanics in general covers motions remain at rest, bodies move around, oscillatory motions, so harmonic oscillators, circular motions, rotations, particle collisions, and we'll touch on all of those as part of this course. Now, I mentioned that it deals with bodies that are subject to force. And there are a couple of forces, and the four main fundamental interactions, or there are four main fundamental interactions, and I'm going to quickly write down their relative magnitude of the forces. And as you probably can guess, some stuff is missing on this slide, and that will happen to a few slides where I'm going to quickly write it down on the blackboard. So the strongest one, well, no surprise, is called strong force. And if we give that a relative magnitude of approximately 1, we can relate all other forces with respect to that, and you can then decide which one of the forces is dominating. It doesn't go very far. It's 10 to the minus 15 meters or femtometers. It holds the nucleus together, and most of ordinary matter. Then there's the electromagnetism. So magnetism. It's basically charged particles. And compared to the strong force, it's 1/137. Electric fields, magnetic fields, electron bounds, yeah.
This is completely unrelated, and I am really sorry.
That's okay.
But is there a force associated with the Pauli exclusion principle?
We'll come back to that later. Pauli exclusion principle means, for those who haven't heard about it, that fermions can't be, two identical fermions can't be in the same place. They have to differ to be in the same place. There are forces associated with it, but we can discuss that separately. It comes later in the course.
Thank you. Because the Pauli exclusion principle isn't the reason that we can exert force at all, James.
Yeah, we can discuss that separately. The third one, now since we had a strong force, someone came up to call another force weak force. That's mainly beta decay. So it describes the mechanism of interaction between subatomic particles that cause the radioactive decay, beta decay. And that's compared to the strong force, only 10 to the minus 5, roughly. And last but not least is what we are usually experiencing in here is the gravitational force. So that's important for masses, and their relative strength is 10 to the minus 39. So quite a lot of zeros compared to the strong force. It's basically attraction between all things with mass, and since energy and mass are equivalent, as Albert Einstein, E equals mc squared, has postulated, all form of energy, including light, can exert a force and feel the force, and that will be part of the course later. But for classical mechanics, we have to limit it a little bit, and that is quickly what I'm going over in the next few slides. So one of the limitations is the particles or whatever we're looking at should not be too fast. The high energy particles at CERN, which the Large Hadron Collider, which I think most of you may have heard of, collide the protons. Anyone has a guess how fast they are compared to the speed of light? Yeah?
99.99.
Yes, you can add even a few nines there. The protons are about 10 kilometers per hour slower than the speed of light. And the speed of light is 2.9 times 10 to the 8 meters per second. So it's pretty fast. And though those are not covered by classical mechanics, we have to use something else there. The usual description when you use classical mechanics, if the velocity we're looking at is much, much smaller than the speed of light. Rule of thumb, physicists like rule of thumb, if it's less than 10% of the speed of light, you can use classical mechanics and neglect relativistic effects. If it's above, you have to be mindful of that. And yeah, if it's too fast, we need special relativity. The picture here shows particle tracks in a bubble chamber. So the charged particle create an ionization track. There's a magnetic field on top of it, and that leads then to these circles, and as the particles slow down, the radius of those circles gets smaller and they spiral inwards. The fastest man-made object is, well, depends how you define it with respect to which object are satellites, Helios 2 or Juno. They are out in the galaxy, and they reach about 10 to the 5 meters per second. It's still much less than 10% of the speed of light, so you can treat them still classically, but that's as far as we get with macroscopic objects. Particles, as I said with CERN, is a slightly different topic. The other end of the scale is not too small. Classical mechanics is valid on scales where the wave-like properties of particles don't become apparent yet. 10 to the minus 9 meters, roughly. So here we've got an image, a TEM image of aluminum nitride, and if you look, or if you know what you're looking at, you can see aluminum and the nitride a little bit in the dark side, and that dark blob down here. So these are scales where one has to use quantum mechanics to understand what's happening there. So if you want, you can do a quick summary of when to use what, and that's always a worthwhile check to do as physicists when you come across something, is trying to figure out what you can neglect, which parts you have to include. And as I said, for example, if you're less than 10% of the speed of light, you can neglect usually relativistic effects. So much, much smaller than c, and we're getting closer to c are those two dimensions, and much, much larger than 10 to the minus 9 meters, and in the order or smaller than 10 to the minus 9 meters, nanometers. So the classical mechanics is usually in this regime. Next. Here, down there, we need quantum mechanics. Some of you probably have already done a little bit, but the course is mechanics. If you're high speed and very small, you need quantum field theory. That's also, if you want, later in this degree. And yeah, relativistic mechanics. So those are some of the limitations. Just quick, if you want to look that up in the paper behind it, I'm not sure of whether any one of you has already come across DOIs, digital object identifiers. Those are for publications and other objects in research, unique identifier. If you plug that in, it will lead you to this paper published in Science a few years ago, where you can read up what's happened in there or why that material is interesting. Now, also, another limitations, not too large. Einstein in 1915 formulated general relativity, the famous equation E equals mc squared, and description of gravity as a geometric property of space and time. What you see here is the effect of gravitational lensing. You have an object here in the middle, which is very, very heavy, and those little bluish rings out here, or those elements here, are actually an image of the same galaxy that is behind here, behind that. So what's basically happening is you've got the galaxy that is in the middle of the picture. You've got another galaxy that's a little bit more bluish behind. We're sitting here on planet Earth, and the light is basically bent around this heavy object. Light is affected by gravity. In classical mechanics, space is flat. In relativity, space is curved. And then you get some nice effects like this here, which you can use then to really peek behind this cluster. So this is all the same galaxy. Okay, so that was kind of the general framing of what classical mechanics is about and what it is not about. And for the rest of the lecture, I'm trying to go over a couple of the basics we will need to deal with the work in classical mechanics. And the key, which we will come across not only here, but in pretty much all other physics, are vectors. And it's pretty essential. Again, I'm probably boring half of you. Others, at least from the feedback last year, said they had never had vectors before coming here. So I'm just trying to be taking everyone along. Here, a scalar is characterized by magnitude only, energy, temperature. Also speed is usually a scalar. And a vector has a magnitude and a direction. So force, momentum, velocity, and if those are the key basics, and the notations, there are various different notations I'm trying to use consistently. One notation, the vector is written bold, which of course is a little bit difficult writing on the blackboard. So another way of writing them is underlining them. And if you have those in 3D, then you write down the three components. So the vector A, what did I put there? Vector A, and then you have a component AX, AY, and AZ, component in X, Y, and Z direction, and the magnitude of a vector is A, or simply A, then not in vector, and that's, now we are at a scalar. And probably not surprising, two vectors are equal if they have the same magnitude and direction. So A equals B if all the individual elements, AX equals BX, AY equals BY, AZ equals BZ. And it's often useful to really draw vectors in examples. I'll come to that later, what it means to set up problems well, so you can actually solve some of the problems graphically. Now, one thing where at least I tend to make mistakes still is translating vector components in 3D, moving up and down. And the key there is to really know what sine and cosine are by heart. So if that's the unit circle, so 1, and you have an angle theta here, 90 degrees there. Let's see whether one can read this. Then this is sine theta, and this length here is cos theta. There is a cheat sheet or a predefined formula sheet which you can use in the exams. It's worth looking at it early on and using it so you know what is on there, and what you don't know and what's not on there is expected that you know, but that helps. And that's of course also one here, this dimension. And just quickly write it out. Sine theta is the opposite side against the opposite against hypotenuse cosine theta equals the adjacent to hypotenuse and the tangent. Those are the main ones we come across, is sine theta over cos theta, and then is, well, you can plug it in, opposite to adjacent. And when you try to work those out in 3D, you basically just have to do that 2 times in series for the px and the py. The pz is straightforward. So if you then work out I'll start with the z component because that's the easiest. So pz, so the z component pz equals p cos theta. So if that's, you've got the angle theta here, and then it's just this element, so the adjacent over the length of the hypotenuse, which is the length of p, gives you the component p z. The x component is px equals, we start again, then we projected 1 down sine theta, and then cos phi. No, in the plane, so we basically project it down here, down here, and then we project it on the x-axis. And last but not least, the y component is py equals the magnitude of p sine theta sine phi. And I've been using the magnitude here a few times. So that is defined as the length of the vector, and that's px squared plus py squared plus pz squared in the direction of tan phi. You can work those out then yourselves. Well, I'll quickly write it down. Tan phi equals py over px, and cos theta equals pz over magnitude p. So these are things you basically have to know in your sleep and get right every time. We'll be working a lot with forces. Vector notation will be important. You will transform them in 2D, in 3D, in rotating frames. And the firmer you are with these basics, the more you can concentrate on the actual physics behind it, rather than having to struggle with this. Next one, unit vectors, a very, very important concept. Unit vector, the name gives it away, is a vector with a magnitude equal to 1. And this is how you usually span a coordinate system. And if you've got 3 unit vectors that are orthogonal to each other, you have what is shown here on the right-hand side. You've got the origin, x, y, z, and the I, j, k are usually the abbreviation for the unit vectors, I in x direction, j in y direction, k in z direction. Their length is 1, and then an arbitrary vector you can make or find out its direction by dividing simply by its length. So this is the vector divided by its magnitude. You get a unit vector into that directions, and you can rewrite any vector in terms of its unit vectors. And if you use different unit vectors, of course the components in x or y or z or whatever units, what axis you choose, change accordingly. We will come across unit vectors a few times, and they are, I think, really, really relevant for many physics problems. Yep, well, let's start again or continue with the basics. Vector addition, vector subtraction, and next lecture we also continue with some. As I said, for some of you this might be putting you off and be very boring, but not everyone is as far as you. So to get the sum of 2 vectors, we have a and b. To find out what the sum of is c. Triangle rule, just put them at the end of each other, and then you get this. So if we have a, b, then the sum is c, so a, b, c in 2D. And we can, of course, take those apart just to be 100% clear, a plus b. So if we take them as cx, cy, z equals ax, ay, az, so the 3 components plus bx, by, bz, and that of course is ax plus bx, ay plus by, az plus bz. Alternatively, if you want to use the unit vectors, you can also write cxi plus cyj plus czk. So those are the 3 unit vectors and the corresponding directions, and then you end up with ax plus bx I plus ay plus byj plus az plus bzk. Well, that's pretty straightforward. Probably not a surprise. Vector addition is commutative, so you can swap the order. That's not the case for rotations. You will come into rotations at some point, and that makes a difference whether which direction you rotate first. Associative, you can put the brackets where you want. It's really similar like the normal standard addition. Ordinary algebra applies. Here, if you want vector subtraction, you can of course rephrase it, A equals B minus C. Note that vector B is then equal to B but in opposite direction, and that helped usually me trying to avoid those, which direction and what point do I usually then attach vectors to get the the difference. So yeah, if you add just the negative to it, you know where to connect them, and then you know, and you end up with a correct result. So that's quite handy. Easy examples of those vector addition and subtraction is, who has played tug of war before? Tug of war meaning you have a rope and people pull. Some people play it with their dog if the dog doesn't want to let go of the toy. Basically, you've got a rope, two people pull at the end. Person A is pulling in this direction with a vector force like that. Person B is pulling in that direction. If the vectors are equal and opposite direction, the resulting A plus B equals 0, and the rope is not going anywhere, and the goal is to move this to one or the other direction. With two people, it's relatively straightforward. Of course, you can expand it and make it a little bit more fun if you've got something like that. Three people pulling. Now, if my drawing skills are not too bad, it is possible if they're all pulling with the right magnitude in the right direction that nothing is moving, because if you add up those three vectors, the resulting, so this is A, B, C, and if I add them up, I'll put them at the end of each other, so I put B over here, add C over there, and if it ends up at 0, nothing is moving. Okay, then last but not least, multiplication of a vector by a scalar. We've already done this with the unit vectors, where we basically just put the magnitude of the vector outside and left it to the side. There the same rules apply. So for any scalars, alpha and beta, and vectors A and B, A and B, alpha, beta, A equals alpha, beta, A equals beta, alpha, A equals A, alpha, beta. So that's pretty straightforward. So it's associative and commutative. Associative and commutative. Then alpha plus beta A equals alpha A plus beta A. So distributive. And alpha A plus B is the same alpha A plus alpha B. So those are the main basic rules for vector. We continue next lectures with some more on basic vector laws. The summary basically of this lecture is to know when classical mechanics applies and what are the limiting cases. Basics of the coordinate system and the basic vector algebra forming the foundation of much of what this course is about. It will get more interesting, don't worry, with collisions and a few other things. But I think with that, we have some lecture notes. Thanks, Duncan. So for those who haven't had the chance to grab lecture notes at the beginning of the lectures, I'll just leave them down here for you to pick up. And otherwise, I think that's it for the first lecture, and I'll see you tomorrow morning at 9 a.m. again. Thank you very much.
Something like